What if your aircraft could fly into the storm when every other system is grounded and still complete the mission flawlessly? Welcome to Industry Ignited. I'm Dr. Leeanne Aguilar, and today I'm joined by Mark Strauss, founder and CEO of Wave Aerospace, a company building next-generation unmanned aerial systems engineered to operate in extreme environments on land and sea when failure is not an option. Mark, welcome to the show.
Well, thank you so much. I really appreciate the invitation to join you this morning.
Well, I'm excited for our conversation and learning all about what you're up to. Now, tell me about your career. I know it spans aerospace, engineering, predictive analytics, marketing, and entrepreneurship. What has been the through line connecting these disciplines for you?
Sure. Probably there's been two strands that have tracked with me through this journey. The first is very personal. I grew up in a family with a father who was an architect and a mother who was a mathematician. And while I often tell people that resulted in a lot of extra therapy, the truth is growing up with both sides of that equation, that creative and then the very linear sort of mathematical background, is definitely something that stayed with me. That said, although my academic background is formally in chemistry and chemical engineering, at the time I was in school, there was a lot of focus on molecular biology and biochemistry. And I really took the path on the other side of the chemistry and the natural science world, which was physical chemistry and quantum mechanics. And those at the time were really focused on statistical functions. I still remember one of my fondest memories was going into a first quantum mechanics class and having a professor write 0 on one side of the board and 1 on the other side of the board and saying, these are the two answers to every question you're going to get in this class. Show your work.
Wow. Yeah, fascinating. Now, you founded multiple ventures before Wave Aerospace. What early experiences shaped your approach to innovation and leadership?
I'm always working on my leadership skills, and I think that I'll speak just for myself, but it always seems there's a long way to go. That said, the common focus among everything, including my time in the classroom, both as a student and as a lecturer or teacher, has been communication. In fact, it seemed to me very early that the scientists and the innovators that people knew best, even among the general public, were the engineers and scientists that communicated most effectively. So I found that communication was really the key, being able to take a complex idea and communicate it in words that people would nod their head and say, well, that makes sense.
Yeah. Right, because it comes down to communication. If you can't get your idea across effectively, then the best idea in the world isn't great. It doesn't get anywhere. And I think that even comes back to the math problem or you're talking about, there's the 1 and the 0 and show your work. I mean, it comes down to communication there too. It's like showing your work. It's showing how you arrived, something, why something works, why something's effective. So I think that communication is a through line I see there as well.
Absolutely. In fact, to this day, I'll ask a group of students a question, and nobody wants to answer because I think they believe that I'm trying to trick them, that there's a
Yeah.
trick answer. And I often have to remind them that, look, before we get started, I'm going to ask you a few questions that you should know and you shouldn't worry about knowing them. They should make perfect sense to you. And this is just to make sure we're all on the same page. Because as a teacher, not a magician, as a teacher, I'm trying to teach. If I can base what I'm teaching or sharing on your own intuition that you've developed yourselves and your existing knowledge, then we've already got a huge head start.
Right. Yeah. And then it comes down to, I mean, as a teacher, getting feedback from your students to make sure that they are grasping the knowledge, that their feedback lets you know, it communicates to you that they get it, right? That they're, yeah.
Absolutely. And yet they still think I'm tricking them.
Yeah, it's not right. Now, tell me more. I know you've been a lecturer at Parsons School of Design and an expert witness even in digital media. How has that blend of technical and communication expertise influenced how you lead today?
Yeah, I spent many years doing those. I've been busy in the last decade or so with other projects, but I spent many years lecturing. And again, it relates directly to communications, right? You're taking a group of people who are not experts and communicating an idea that may be something completely new to them, or maybe something they know a little bit of, and communicating it in a way that they can understand, grasp, and see the connection to what they're doing. I mean, the fact is, my first lecture at the New School or Parsons, every one of the students in the program is a better artist than I'll ever be. So when I communicate with them, I'm not able to communicate how to be necessarily a better artist, but to help them understand how communication and how thinking about things they may not have thought about. For example, does the name of their company read well from right to left as well as left to right? Or does it spell something terrible from right to left and it doesn't spell from left to right? I mean, these are things in today's world that are really important.
Yeah, it's that psychology aspect of it, and in marketing, it's all about communication too in psychology. I relate to that a lot because you have to be able to make sure that what you're designing, whether it's art or marketing pieces, which is artwork as well, that it's effective. It's conveying the message in the way that it's intended. Because if you're not right, communicating intentionally, and if that message isn't landing, then that communication is lost, or it can sometimes even backfire and work against a company, like you were saying,
Uh,
if it's unintentional
Absolutely, absolutely, and
consequences.
especially in today's world where we're dealing with languages that get transliterated. In other words, they don't go from our alphabet directly to just a different word. They actually may be in a completely different alphabet, unrecognizable as our alphabet. Then they get transliterated, not translated into our letters, right? So we can pronounce it. Often, if you don't look at the transliteration, you never really know what it's going to spell in our letters, even if it sounds right.
Yeah.
And there's been a number of incidences where that has led individuals into faux pas, let's say. So yeah, it's absolutely important. It's also important from a safety standpoint because remember, our products are being used all over the world, and they have labels on them too, instructions, serial numbers, up, down, right, left, things like that. And that's the reason pilots say niner
Mm-hmm.
instead of nine. Nine in German is no. And it's
Ah.
such a base piece of language that although English has been adopted globally as the language of aviation, we still count one, two, three, four, five, six, seven, eight, niner. And that's to avoid that conflict.
Right. Yeah. Language is important, and small things like that, like you said, can have huge consequences. So, yeah, interesting. Now, at what point did you identify the gap in UAV performance, particularly in extreme weather, and decide to build a company around solving it?
Actually, in the beginning of Wave Aerospace, which was about 10 years ago, our experiments and the work we were doing is really focused on efficiency. So we were trying to take small, even toy multirotors and have them be able to fly for longer. Because at that time, you would fly for 2 or 3 minutes and then you'd have to charge the aircraft for an hour. And that just wasn't something that was going to be acceptable. The ability to fly in bad weather became apparent later on as we were doing experimentation with these, and initially was a side effect, and we've been able to build on that from that point.
So I know that you mentioned that your idea for starting the company actually evolved from an actual toy. Tell me a little bit more about that, and then how it evolved into the core promise of the ability to fly when others cannot.
Sure, absolutely. I mean, just cost alone meant that all of our initial experiments were going to be done on small multi-rotor aircraft toys that we could get our hands on. At that time, they were relatively expensive. As we developed the system, what we found was that the aerodynamics that NASA and JPL and 100 years of work on airplanes had developed were really good. We couldn't add much to that. But what was new was the power system, right? The electric motors and the electric system in the aircraft, and it became very apparent that that's where we should focus. Not so much on the shape of the propeller, which there had been much research on, or but actually on the motor and the battery and the electronics and the computers that handled the power, the energy from the battery all the way to the.
Okay, so the key engineering breakthroughs are it's really more around extending the life of the battery and making it so the aircraft can fly for a longer period of time?
That's part of it, and we certainly look, the more energy you put in it, the longer it will fly. It actually turned out that our breakthroughs and our contribution is moving the electricity from wherever it starts, moving the energy to where it ends, which is the propeller. And in fact, even on our power grid, if you add up all of the energy that we use in the United States to power the country, all of the energy contained in the fuel and in the wind and solar, by the time it gets to your socket and you can plug something in and actually run something on it, only about half of the energy that we started with is available.
Oh, wow.
More than half is lost en route.
Mhm.
And without going down that rabbit hole, that's what was going on, in fact, in the aircraft. There were a lot of energy being lost en route between the source of the energy or the electricity, which was the battery, and the final use case, which was turning the propeller. And that traveling and the losses associated with it were where we ended up focusing.
Interesting. But yeah, that's fascinating that half of the power is actually lost in our grid system. That's a lot. And so is your technology potentially transferable to like the grid and to other technologies?
It absolutely is in many ways. Of course, there's been a lot of work on the grid. And remember, it's not just the grid. If you have gasoline or diesel or coal or nuclear or wind energy, we're taking that fuel, we're converting it, right, to mechanical usually, and then finally electricity. That's part of that process as well. So the loss exists all the way from the energy contained
Mhm.
in the fuel through that process of making it into electricity, and then it continues through the grid. So it's the entire picture that
Right.
is the problem. So when you think about an aircraft and electricity, you have to think about everything from, in fact, even charging the battery, right? Because you're gonna at some point need to charge that battery as well. And ultimately, that charging of the battery goes all the way back to the coal or oil or natural gas that's producing the electricity in the first place. So you can imagine all the conversions that
Yeah.
have to take place to get these small devices or large devices that run on electricity into the air.
So how much more efficient have you been able to make your system?
This is a really interesting question. If you simply hover one of our aircraft next to many of the others that are around that you've probably seen around on the news or otherwise. We don't necessarily hover for the longest time. So, in fact, you can specifically design an aircraft to use very little power to keep itself in the air under certain conditions. Where we really, so it's a little bit of a difficult question to answer. Where we really shine and where we have to test our aircraft is in an actual mission. In other words, with the wind blowing.
Mhm.
The aircraft actually uses power very differently from when it's flying on a mission than when it's hovering in good weather. And that should make perfect sense to everyone because we know that cars have city miles and highway miles,
Of
right?
course. Right.
It's absolutely the same thing. So when you ask that question, where we have really concentrated is on that city mile aspect, right? Where we're actually aggressively
Right.
fighting the wind or the conditions or making maneuvers,
Mhm.
not just hovering in one spot.
That makes sense. And because I know your platforms actually operate in force 10 ocean conditions and high wind environments, like you said, what design constraints had to be reimagined in order to achieve that level of resilience?
That's also a very interesting question because we have a lot of freedom in design and size and scale and how big we can make things. And still, we don't take a helicopter from New York to LA when we travel. So, that's not because we can't build a bigger helicopter. So when you ask about design constraints, the biggest design constraint is the thing we can't change, which is the atmosphere, the air.
Mm,
So the molecules of air, the oxygen and the nitrogen and the way it interacts and the way it flows is the main constraint and actually dictates everything from the shape of the aircraft to the size and weight of the aircraft. There's a reason we don't have 100-foot wingspan birds, right?
right.
There's also a reason why small planes don't look like big planes. The reason is you would think they would figure out which way and one works best and just use it. But the problem is the atmosphere doesn't change.
Hmm.
At least not massively. So the biggest single constraint we have to deal with is the fact that the air, for the most part, it changes density up and down, but the air, for the most part, the size of those atoms and the way they flow is not something we can easily impact. And so that's the primary constraint we deal with at all the sizes and scales that we build.
Yeah. Now, the hybrid architecture you've developed challenges traditional rotorcraft and fixed wing limitations. How does your platform fundamentally differ from conventional UAV systems?
There are some very obvious things you can see in the aircraft, but fundamentally, we try to reduce the number of changes and the size of those changes of the electricity flowing through the system. So, whenever electrons move through a wire, or we can refer to it as electricity moves through a wire, there's losses,
Hmm.
right? And the greater electricity or the more current, the more watts we push through that wire, the greater those losses, and it's not linear. So we have two factors pushing against each other. On one side, we want to reduce the work we have to do in terms of how much energy we need to keep that plane stable and on its mission. And on the other side, we have to still be able to keep that aircraft stable and flying, which requires a certain amount of force or power. So there's always a balance of how do you maintain stability and reliability, making the least changes in, let's say, propeller speed. It's
Hmm.
sort of like driving on the highway. I play a game. I have to commute to work, and it's a game that I love to play. And I try to play it as safely as possible. So I was always taught when I was driving on the highway to look far ahead so you could see what was going on ahead of the car. I try to make my 30-minute commute push on the highway, pushing the brake as little as possible. So, in other words, I look way ahead so that instead of hitting the brake, hitting the gas, hitting the brake, hitting the gas, I can take my foot off the gas early enough, not so much to interfere with traffic, but so that by the time I reach that point where I have to slow down, I'm already going the correct speed. That's the basis, if you can imagine, for how we work these aircraft, and that's where the predictive element comes in as well. We want to predict how
Hmm.
we are going to have to move that energy and how much energy are we going to need when.
So it's looking far enough ahead to be able to predict. And so, how does that work inside of your technology? Like, how do you incorporate that?
Well, of course, that's the magic that's the magic question. But actually, there are some basic ways that we can do that. And one of the ways is since we don't have people on board, we don't have to keep the aircraft perfectly straight at all times. We're not going to have a drink slide off the table. Small perturbations that don't endanger the aircraft or the mission aren't really a problem. So one of the things we need to do is we need to take what's going on with the aircraft, and of course, like all aircraft, bounces around to some extent, and we have to make adjustments for understanding exactly how much we have to intervene to keep everything safe and reliable. And one of the ways we do that is using something called a tuned mass damper. And the reason I bring up this sort of high technology term is because it's one that is actually used, though a lot of people don't know it, to protect buildings from earthquakes. So a great example, if any of listeners want to look this up, in the building Taipei 101, which is a big skyscraper. At the top of that building is a giant mass, a ball, a metal ball, and that ball is suspended at the top of the building, which seems crazy. You're putting a heavy weight at the top of the building,
Yeah.
but if there's an earthquake, the earthquake tries to shake the building, but that ball doesn't really want to move. We take a lot of the key heavy parts of our aircraft, and they are in fact suspended in a mechanical way inside the aircraft so that when the aircraft wings, the part you see is perturbed, maybe even violently. The key elements, the sensors and the mass, like batteries or fuel that is contained in that aircraft, is actually in a position to function as stability, sort of like driving a heavy car versus a light car in the wind. It helps
Right.
keep that aircraft stable. So we use the mass of the aircraft itself to help overcome that instability that is the aircraft is exposed to. By
Got
using
it.
the inertia in that mass, right, how hard it is to move that mass, that's we don't have to use electricity to speed up the propellers to do it. That was a lot there, but I'll let our listeners look up Taipei 101 and see how that works. But if you imagine we use that same system, a tuned mass damper. That's
Yeah.
one example of the technology that we use to address this problem.
Oh, super interesting. Yeah, I'll have to look up that building as well. That's fascinating. Yeah, something suspended at the top that's super heavy. I guess that does make sense how it would, work to stabilize in a, earthquake, weather
Sure.
or
It's hard to
environmental
move
condition.
heavy things, right? I
Yeah.
mean, even if something heavy was very small, if it has a lot of mass, it's hard to get going. And in an earthquake, which is an instantaneous event, that big mass does just that. It helps stabilize that building. And so really, again, far away from the aerodynamics, but very key to how much electricity or how
Yeah.
much energy we have to use to keep that airplane stable.
Now, your systems are payload agnostic and mission configurable. How does that flexibility create strategic value for defense, law enforcement, and commercial operations?
Sure, and that's a two-part question, but it's both parts I think are equally important. The first is very straightforward. We hear all the time how fast the technology is evolving. However, we've seen propellers on airplanes for nearly 100 years. So clearly there are aspects of the aircraft that evolve faster than others. I know the shapes of the propellers change. The payload agnostic nature of our airplanes is simply to allow those payloads to advance, those sensors to advance as quickly as they can and allow us to integrate them without having to redesign the whole plane. So as payloads get more sophisticated, we provide communications and power, and we can take advantage of that quickly accelerating technology. So that's one side of it.
Mhm.
Okay. The second side is very significant and is the first time in this conversation that we're treading on a very sensitive subject, which is the protection of life. We are not a weapon per se. We go both ways, right? We go out and we come back. If you
Mhm.
look at drones on the television, nearly every one you see is designed to blow up when it gets somewhere. And we don't do that. However, when you launch something like a Tomahawk cruise missile, the decision, and this is not a political conversation, I'm not questioning why, but when that missile is launched, the decision to use the missile has already been made.
Right.
Now, it might be in the air for almost an hour before it hits its target. It's a subsonic missile. It could be flying 1,000 kilometers. And during that hour, a lot can happen in a complex environment. We want to delay the decision of whether or not we're using a lethal machine. And so our aircraft, and you talked about the agnostic nature of the aircraft, our aircraft, if there's something going on, can take off immediately because we're not giving them a target to blow up or to go attack or to give instructions. We're taking off what in essence dates back to that toy a decade ago. And it can go look and it can go sense things with its sensors and it can send all of that information back in a very non-threatening, low-speed fashion. We can even hover a distance away, which is, a very non-aggressive thing to do, but we're moving the decision of what has to be done, if anything, all the way out past the time it took to get there to that point where whatever's going on, a decision has to be made. So, for example, if there's a container ship carrying lawn chairs that's on the water and it's going around, we certainly don't want to blow up that container ship. Right. But if one of those containers opens and there are missiles in it, and again, I'm not getting this is not related to anything that's going on now, just the fact of the science. When
Sure.
we see those missiles, we're already out there. In other words, we've already traveled that hour, right?
Right.
And we don't have to wait at that point. We can retask the aircraft. So these aircraft, while in a normal day return home and land, they have the ability with additional information that's extremely timely
Mm-hmm.
to say it's not 80% chances missiles on that boat. There's 98% chances missiles on that boat. And it is our hope, and we are designed to move that retasking as close to the decision point. This has a term, called the kill chain, and I know that's a touchy term because it has the word kill in it. Our goal, of course, is not to kill things that we don't have to, but to move the kill chain to the decision as close as possible so
Mm-hmm.
we can make that decision later. So that's very basic to what we do. Whether or not we're involved in any kind of engagement. It very well may be that we return home and don't interact with the target, but we have sent timely information
Right. Which
that
gives
is,
more
yes,
options.
exactly.
You have a lot more options, and not only that, but you're sending back better information. So they're able to make better decisions with more time available.
Absolutely. And that takes the AI. It doesn't mean we don't use AI,
Mm-hmm.
but it allows human beings to interact with that kill chain on a faster time scale, which ultimately can have other side effects. This is in no way anti-AI. AI is critical to all of these missions. But remember, the more we can process, just like you said, the better it is.
Yeah. Now, as you mentioned, you're operating in high stakes environments, defense, ISR, logistics, where reliability is mission critical. How do you approach trust building when customers or with customers in these sectors?
Extremely carefully and with a lot of hard work. That starts with using the materials and screws that would go into any normal military airplane. And it doesn't matter whether the police are using our aircraft or the Coast Guard for search and rescue. They are built to military standards. It means the metals that we use, whether it be titanium or certain types of stainless steel, are very carefully considered. It means that aluminum can't touch carbon fiber, for example, because there are chemical reactions that go on. So that's where it starts. But the difficult part is that actually going out in the field with active duty personnel, and that again could be the Coast Guard, it could be the police, or the military, and actually demonstrating these aircraft and letting them use them in these conditions is the primary way that we have to do it. And we actually spent last spring a month down at Fort Benning working with active duty personnel in the woods, in the rain, high stakes, simulated live fire, showing that these systems don't fail. And ultimately, when it comes to the military, that is the primary and I think best way to build confidence in the platform. It makes it hard for us, but
Yeah.
it's the way to do it.
Right. Actually demonstrating, right, the capability is actually getting out there and interacting with their testing. Yeah, that makes sense. All right. So, with platforms like Mule and Huntress pushing boundaries in endurance, payload, and speed, where are you seeing the strongest market demand today?
Sure. We're seeing an incredibly strong market all over. And not to take away from the incredible work and aircraft of the many companies that are out there building these, but the demand is focused on the scale of the aircraft we build. So although we're building aircraft in the 50 to 1,500 pound range, even the larger aircraft are built to not require ground support equipment. So as we expand as the Earth and as we learn our world gets smaller and smaller, we start to explore places like the Arctic and the Antarctic. It's very important that we have aircraft that are self-sufficient. So our Mule, for example, can land like a hybrid car. It doesn't need a supercharger. Its own hybrid system, its own engine can charge its batteries, and it charges its own batteries. So you can give them fuel and they're ready to go. You don't need a launcher. You don't need a truck. They are really designed to operate in any environment without having to get into that environment by road or first. So the demand is extremely high at all levels, and especially now that operations, both exploration and others, are taking place at more and more remote areas around the world.
Very cool. Now, as global environments become more unpredictable, like climate, geopolitical, operational, how does that shift the role of UAVs in modern operations?
I think the shift is being driven by both the unpredictable nature of the geopolitical environment, and that includes things like communications and global navigation interference. But it's also being shifted by the fact that we're exploring more of our planet, and the last places to explore are usually the hardest. And so just like NASA put a helicopter on Mars, what's being realized is that aircraft, especially small aircraft, can carry the sensors that we need to get to places and look at things that historically would have taken incredibly large, expensive missions. And now we can do that very inexpensively. And ultimately, it saves a lot of time and money, but it also, for example, saves its impact on the environment. It's a lot different to fly a 1,000 pound uncrewed aircraft over a sensitive area than it is to, drive or build a base out there and leave all of the effects that would be necessary to do that.
Yeah. Now, you mentioned the challenges around with people spamming or spoofing and jamming the global navigation systems. How do you approach that? Like, how do you solve that?
Sure. Well, it's funny. I learned to fly before I could drive, and it was an amazing experience. I am a civilian pilot, though I've flown my entire life, and flying the airplane on a good day from point A to point B is you learn very quickly. In some ways, it's easier than driving.
Hmm.
Most of the time you spend is what do you do if things go wrong? And how do you keep things from going wrong?
Right.
So from a young age, my philosophy with all transportation and aircraft has been let's just assume everything is going to go wrong. So, although there's been a lot of talk about, what happens if you lose global navigation, if it goes away, from the first aircraft we've built many years ago, we had made those assumptions right off the bat.
Mm,
So we had made assumptions that we were going to have our communications jammed, and we made assumptions that we were going to lose global positioning. We made assumptions that visibility was going to go to zero because ground fog would come in or some kind of fog. And
right.
so these have really strengthened our offering, but they didn't change very much what we were doing. So all of our planes, for example, even our smallest aircraft, contain inertial guidance systems, which are guidance systems like submarines use and spacecraft use, where there is no global positioning, there's no GPS. And although we do rely on GPS whenever we can, and it's a great system, the ability not to worry about what happens if we can't use it is a great freeing aspect. And almost every system on the aircraft is not just redundant, but assumes that from the beginning that we're going to lose these things. Like visibility, for example, we talk about avoidance.
Hmm.
Well, almost all avoidance systems on small aircraft are visual. I mean, even in a small airplane, we often don't have radar. We have visual scanning of the sky in front of you. And we have ATC, luckily, to help us with that. We have radar built into everything. And while it's not a complete replacement and it's different, it means that if suddenly the landing strip becomes obscured, we will be able to land that aircraft, or the computer will be able to land that aircraft safely where it's supposed to go, where it's expected to go, and we don't have to worry what will happen. So that's been sort of a central tenet, and it came from my early experience and ongoing
Yeah.
experience with aircraft, because your radios fail on aircraft too.
Right.
Right. And there's a whole procedure of what to do. So it's not that much different than would be the bar for the last 100 years of development of regular aircraft.
Yeah. Yeah, I see that. So, what are the biggest challenges you face scaling a deep tech aerospace company, particularly in terms of capital, talent, and regulatory complexity?
Sure. I think historically there was a lot of, and historically only goes back in this space 20, 30 years before, the FAA had to get significantly involved. I think historically regulatory environment has been difficult only because the tech accelerated so quickly.
Hmm.
We have not had significant problems with the regulatory environment. Again, safety is our number one concern, which is generally what the regulations are there for. Everything we do is built on reliability and predictability. And so, even with regard to the FAA, we maintain a COA, which is sort of an extended waiver to operate our aircraft close to the airport or inside the airport where we build the aircraft. And of course, we deal with air traffic control like any plane would, but the FAA has acknowledged that, we do not interfere with operations at the airport and we are reliable. And they've interviewed air traffic control to make sure that's the case. The biggest challenge for us at first was communicating that the aircraft behaved differently, and this remains a challenge to the people who are building both the payloads and our users, right?
Hmm.
Because quite honestly, a decade ago, if you asked me if multi-rotor aircraft were a good entrepreneurial business to get into, there was no doubt there was money there, but you were getting into a zoo. There
Right.
were regulatory problems, there were thousands of competitors. And as an entrepreneur my whole life, I would not have wanted to get into that space. So differentiation has been, and you hear that a lot, but differentiation has been central
Right.
to our work. And then the final difficulty, which is true of any significant aircraft, when we're talking about large aircraft, they are in the range from a cost perspective of $1 million and up. They're the size of a car. So when you're scaling, and I think it's not a quote, but I believe Elon Musk at one time said one of the most difficult projects he did was setting up the production of the Tesla
Right.
cars. And that's the same for airplanes,
Hmm.
setting up the production of a large machine so that there's quality is maintained and standards are maintained and there's oversight is really one of the biggest challenges now. It's expensive, but even more so, it's just a large scale operation that requires a lot of very, very dedicated people.
Now, you said that your aircraft are between 50 and 1,500 pounds. Is that right?
That's correct.
And so, what license is it? Just the UAV pilot license that you need to fly your aircraft?
No, and this is where it starts to get a little bit of complicated. We built our first aircraft, our Falcon, so that it fit under the Part 107, which is the standard drone FAR rules from the FAA, so that municipalities like police and emergency services could use it.
Hmm.
The larger aircraft do not fall under that category, nor do their abilities allow them to fall under sometimes even higher categories.
Hmm.
So, for example, even large jets flying into New York area, when they're below 10,000 feet, they have to fly at 250 knots or less.
Hmm.
Our aircraft, our Huntress, is capable of flying significantly faster than that, which changes their category of what they're capable of into a world that really hasn't been specified yet.
Oh.
And so the result is that we communicate with the FAA, but often much of the testing,
Hmm.
again, not with armament, but much of the testing for flight testing has to go on in protected Department of War areas or missile test sites that are dedicated for the testing of complex systems.
Right.
Now, we're not testing it there because we need a range where we can blow up a bomb, but we're testing it there because we know there's nobody else there, and the FAA has, can sort of take a step back.
Yeah.
So that is a challenge.
Yeah. Right. Absolutely. Because they fall outside of, like you said, the normal drone specifications, or is it part the 107, or I
Yes,
forget.
Part
I have
107.
my drone pilot license, but remember all the,
And that's
but
gonna
they're for small. Yes.
change, right? In
Yeah.
fact, when the FAA comes in and specs our facility, and they see turbojet engines, already it sets off all kinds of
Hmm. Yeah.
mental alarms, I think. And I can still remember the first time they visited. Now, like I said, we have a very good rapport with them, and they know that we behave predictably and responsibly. But yeah, it is these aircraft, the flight envelope, which is the speed and the
Hmm.
altitude and their abilities, are truly outside, which is
Hmm.
why we build them, of anything that exists. And therefore, the rules don't always match up. And in those gray areas are where, it
Yeah.
gets.
You've described yourself as combining predictive analytics with aerospace engineering. How does that mindset influence how you anticipate industry shifts?
That's a double question again, but let's start with the latter half of that, which is industry shifts, because that I think is the biggest driver of what determines where the company is going on a strategic level. We are students of history. We look back and say, how has transportation shifted over the last 100 years, over the last 200 years? And one of the interesting things about aircraft is that despite the fact that they seem very different, they've really come along together. Aircraft and cars in the early 1900s came about and evolved over the 20th century quite in lockstep. And when electric motors came on the scene and the ability to store large amounts of electricity or energy on the airplane became available, we saw electric cars and electric airplanes, and we're seeing that now evolve once again together. So there's a lot of history behind how these different power systems interact with different transportation systems or different ways of moving through our environment. And so that's one of the ways we look at this. The other way is to look at related industries. So we follow battery tech very closely, the ability to produce electricity from chemical fuels. What are the hard limits that we expect to see? When do we expect to see shifts in the amount of energy we can carry? I mean, the bottom line right now, and everybody should take this to heart, is that on average, a drop of fuel, or let's say a kilogram of fuel, carries with it 40 times as much energy as a kilogram battery.
Okay.
In its
Wow.
best case, 40 times. So there's a huge challenge in front of us.
Hmm.
We also have to keep in mind that a kilogram of fuel, of gasoline, is a particularly dangerous thing. You can't take it on an airplane, right? That's why they take away your bottles. You can't take
Right.
a bottle of gasoline on an airplane, probably for good reason. I'm not questioning that. But if you put that much energy into a battery, it begs the question, can you take the battery on? So right now, batteries hold less energy and they're very convenient. If you pack a lot of energy into that battery, well, it's great for us for flying airplanes with no people on them. But now you have people with laptops that don't have to be charged except once a month.
Hmm.
But if things go awry, there's a lot of energy. We always say the more energy you jam into the battery, the more that comes out when it breaks, right? My point there, relative to your question, is it's not a simple predictive equation. In other words, coming up with a better battery doesn't necessarily solve the problem. Now, for us, with nobody on the plane in a war environment or over water, it may be a benefit, but remember, the battery industry is driven primarily by consumers and by the grid, by
Hmm.
the power demands. And that's really what's going to move the industry forward. So just because of the science advances, it doesn't mean the use cases will at the same speed. And that's where the predictive analytics comes in. We've already talked about predicting how the plane will behave in the air and how that helps us save energy in the air. Predicting where the industries that drive saving of energy in the air, that's a different story. And we use a set of tools that we've developed to do that. That is maybe fodder for another day. But it is looking at these industries is very important, even if they're outside aviation.
Yeah. Now, are you using lithium batteries?
We use all different types of batteries and energy storage. We also use batteries, so yes, but not solely. We also use, because there's two parts to the battery, right? There's how much energy you can store, but then how quickly it will give it off. So there are batteries that will last 10 years,
Hmm.
but you can only take a little tiny bit of power out of them at a time, right? And so in an aircraft, we have the challenge that sometimes we don't need that much power out of the battery, but sometimes we need staggering amounts of power,
Right.
like
Yeah.
on takeoff, right? You could feel it in your tummy, right? When you're
Sure.
taking off, there's a lot of power coming out of those engines, and uncrewed aircraft are the same. And
Mm,
so the challenge is we do use lithium. We modify the batteries that we use. They are made in the United States. The cells are made in the United States. We modify them so that they give off just the right amount of energy that we need in the most efficient way.
awesome. Yeah, I'm just thinking about all my little drones and how the takeoff and the batteries, and they have gotten better over the years. I mean, I would say the batteries these days are much more efficient than the
Absolutely.
drones I had even a couple of years ago. But now they're a lot more sophisticated with the cameras and the multiple abilities that they're offering, and so it's pretty awesome. Uh,
Absolutely.
yeah. So, Mark, as autonomy, AI, and edge computing continue to evolve, what does the next generation of unmanned systems look like?
That's a really great question. When I was in school many years ago, we were talking about AI, right? So I know AI is still being spoken about, and I know it's very different now. I'm not naive to that. However, I mean, we've been looking at, HAL taking over the world or a spaceship in 2001, the movie, for many, many years, and we've collapsed the all the work that's been done into this idea of AI, right? So if we had a bubble or a Venn diagram, AI has now grown to this huge monster bubble from the 1950s till now. However, one thing that has changed massively, and I think is initially having the most impact, is edge computing. And basically, that's because computers have gotten so powerful and they use so little energy
Hmm.
that we can take what just decades ago would have been illegal to even export, and we can put it on a plane with almost no impact. What that does is critically important. I guess I'll keep this to one main point. The sensors on our aircraft and on almost all aircraft at this point collect an immense amount of data. Enough data for research to be done for decades. NASA talks about that. From a telescope, they get data that's enough for decades of research. We can't communicate all of that data to the ground to make it usable and then back to the airplane quickly enough. So we need to process that data on the plane to make it usable, to make it helpful, to make it more helpful.
Right.
And so when we talk about edge computing, the ability to take that incredible amount of sensor data and process it at least to a point where it helps us make a decision about the current flight. That is absolutely critical. Not only is it critical in keeping that airplane in the air, it's critical in avoiding counter systems that may be there to keep you out of a certain space. It may be able to pick up changes in what we've expected to see. It may be able to say, hey, look, don't hit this target because it's not a target, it's just a school,
Right.
right? That is edge, the impact of edge computing. And again, if we fired that missile with permission to blow up an hour before, we don't always have that information. And
Yeah.
I'm not getting political here. I'm just using current examples. I'm not
Examples.
saying, so please
Right.
don't. Everybody doesn't have to write it, and I do understand. I'm not taking a position. What I'm actually saying is that having the computing power on the airplane makes a huge difference in say everything from saving power to saving lives.
Yeah. Yeah. No, I I get that, and that's a huge advantage and benefit going forward, especially, yeah, considering current examples like you're saying. So finally, Mark, for founders building in highly technical, high-risk industries, what advice would you give about navigating uncertainty while still moving fast?
Be safe. That's number one. I just posted something on LinkedIn. One of the systems that took the longest to develop on our Mule aircraft, which spins large propellers near the ground, is the on off switch. So that when it's off, because remember, these are autonomous aircraft, which means it could be sitting in the middle of the desert with no one around it and suddenly take off,
Yeah. Yeah.
right?
Right.
So the first thing I would say, and now this doesn't go for every industry, but we're talking about aircraft here. As these aircraft scale, to be safe, and if you're in a system or working with a system where there's not that physical danger, understand that the things that have been successful and the reason our company has been successful is because what we build works in the real environment. One example is even at night, we were out in the desert. Everybody was going home. Everybody's putting their airplanes away in the trucks that they came in. We just left our aircraft standing in the desert. We came back the next morning and they were covered with snow. Okay. If that isn't part of your plan, right? Whether it's a little encoder or earphones, human beings now are out and about more than we've ever been. And we're in different environments, and everything from clothing technology to shoes have allowed us to do that, which is fantastic.
Right.
However, the devices that we use, I mean, I'm still wiping my glasses when I'm out in the rain because nobody's figured out how to, do the little glasses, a windshield wiper thing. But keep in mind that these things can't just work in the lab. They might be designed and tested initially in the lab, but they need to be able to work
In the field.
reliably
Yeah.
in the field, and the field as a we work with military people. My father was in the military. I am not a veteran, but I have great respect for the men and women who work in all aspects of protecting us. And let me tell you, they work hard and they work 24/7 in every condition.
Hmm.
And if your device for them doesn't work in the conditions they work in,
Yeah.
then you need to go back to the drawing board. And that's what has driven our success. And it's driven our relationship with the FAA because they know they can rely on us. And it's driven our relationship with the DO because they know whether it's raining or snowing or freezing rain, that they turn on that airplane and it's going to work. It's going to do what it's supposed to do. As mundane as that may be, it's going to do it successfully.
Absolutely. So yeah, going back to your mission of having, yeah, aircraft that work in places and situations where others don't. Yeah. Well, Mark, thank you for joining
Terrific.
me. Yeah. How can listeners learn more about you and Wave Aerospace?
Sure. Well, they can always visit waveaerospace, one word.com. And they should feel free in contacting either the company or myself, Mark Strauss, on LinkedIn. Please do. I get a lot of requests to connect, and I'm delighted. Thank you very much. But please write a short note and just tell me what you're interested in. And I'd be happy to connect on LinkedIn and often have a conversation from there. We're here to serve an awful lot of people that are out there, and the more people that share their challenges with us, the better we can do that.
Yeah. All comes back to that communication again. Right.
Absolutely, absolutely, and we really take that to heart. So, if you don't get through the first time, it just means that we failed, and try again.
Yeah. Well, thank you, Mark. I really appreciate the conversation and yeah, learned a lot. Very fascinating. Yeah.
Well, thank you.
And to our listeners, thank you for tuning in to Industry Ignited. Be sure to subscribe and join us for the next episode. Until next time, stay bold, stay curious, and keep igniting industry.